Welcome, welcome, welcome. Good morning, good afternoon, or good evening. My name is Mr. Kanwar. I previously did the space topic with you, and now I'm here to do energy. So we're looking at energy, lesson 1, and we're talking about energy stores. Hopefully you found the intro rather energetic, if nothing else. The challenge today is to give examples of different types of energy stores. Some you may already know, but we will go through some that perhaps you do not know. And the aspire is to explain how different types of energy stores can be increased or decreased. That is what we are learning today. So, as with all my lessons, what do we need? We just need a paper or with a pencil or a pen. You don't need anything else. You will need a ruler later because you'll be drawing a table, but nothing else is required. Now, your starter task. Your starter task is something that I want you to think very carefully about. And it is, what is energy and can you describe it? That's what I want you to do. What is energy and can you describe it? I'm going to give you a small hint. That image is of a snooker ball, a white snooker ball hitting a red one. And the second is of a steam engine. You have 30 seconds to write down anything that you think. So I want you to describe what is energy. And your 30 seconds starts now. Right, there we go, time's up. So what is energy and can you describe it? Bizarrely, I'm not going to give you the answer to that question. I want you to think about it. Keep it next to you, but over the next couple of slides and approximately 5 minutes, I'm going to explain what is energy, because I think it's quite a hard concept. You know, that first hint, you've got something moving, you've got something stationary. What is the energy there? Is it the fact that something is moving? Is it the fact that something is being transferred from one to another? Because we know as that moving object hits that stationary object will move, won't it? And how is that linked to that steam engine? Well, we'll find out. And before we start talking about energy itself, we need to understand the history of energy as a concept. And the question that I posed you for your starter is the same question that was posed by Mr. Leibniz with his funky hair. Now in 1676, I should say, he was thinking on the same lines. What is occurring between two snooker balls? So what he attempted to describe and explain is what got transferred between the two snooker balls when one was stationary. So going back to that image, and he decided to call that movement or that transfer a living force. So he said that a living force got transferred from one ball to the other in a collision. So he called it the living force, and obviously this is in the 17th century. However, by 1806, 126 years later, a chap named Thomas Young, and here he is, he first used the word energy to describe the situation that Leibniz described. So he was describing two snooker balls. He described it as energy. So he didn't call it the living force. He now described it as energy. It didn't catch on, to be honest. He was quite a shy, retired guy, Mr. Thomas Young, and it didn't really catch on until 50 years later. So, but the question is, I go back to that, and the reason why I pointed at 126 years, what happened in that 126 years for Thomas Young to describe the word as energy from living force? And what occurred what this great image shows is something called the steam engine. Now we probably know it, but may not know much about it, if you see what I'm saying. We know what it means in terms of it runs trains and it runs automobile. Well, it used to run automobiles and lorries and so forth. However, during the Industrial Revolution, it absolutely changed the landscape because you were able to maneuver items, infrastructure, materials from one end to another, and enabled the Industrial Revolution, which allowed Britain, in particular, to become a colonizing country. And this occurred in the 18th century. What has this got to do with energy? It's all got to do with energy, but it's got to do with some other person who is Nicholas Carnot. So he lived during the Industrial Revolution, or just at the back end of the Industrial Revolution, and he lived in France, Napoleonic France. So Napoleon was the emperor during that time, and Napoleonic France saw Britain as great rivals. Such great rivals that Carnot, as a physicist, thought that the advantage Britain had was due to their steam power and the fact that that enabled them to, like I said previously, to shorten time to transport goods. And that's really important. If you're able to transport goods, materials, supplies to the front lines, you're able to supply your armies much quicker. And that's what he was looking at. What is it that Britain had that allowed them to do that? And it was the steam engine. So he wanted to uncover the fundamental nature of the steam engine. And what he realized was something quite simple, I think. Basically, that energy flowed in a system. So basically you've got a system. Within that system, you have a hot source, or this is the steam engine. You had a hot source and you also had a cooler source. So the image that I've got here is your hot source and here is your cooler source. Now I'm just talking about objects. I'm not talking about literal, like I'm not talking about smart ketchup or anything. I'm talking about objects here. So with your hot source here and your cooler source, there is a temperature difference between them. Okay, there is a temperature difference, and it kind of flowed. That energy kind of flowed like water. So it would flow like down from here, and you could take that energy and you could use it, and they used it in this sense for a spinning wheel. Okay, so it flowed like water and you could use it for a third energy store. And that's what he discovered, quite simply. However, Carnot went one step further. Not only, and going back to the same image, not only did he realize that energy, or the flow of the substance, could be tapped by diverting it. So, going back to this image, we could use it for the spinning wheel to do useful work, and you may have come across that term, but the idea of doing work is using your energy in a more useful capacity. He realized to make the heat engine more efficient, what you needed to do was you needed to have a larger temperature difference. If you had a larger temperature difference, you would make it more efficient. And you can see now that the spinning wheel would go around quicker. And the reason being is because you've got a larger temperature difference between source 1 and source 2. Because you've got a larger the temperature difference between those, so the flow of energy, or the flow of this substance, would be quicker, therefore spinning the wheel quicker. And it's this diverting towards another energy store to do useful work, which is what effectively the steam engine used to do. And they used to, pump. It would pump the coal into the furnace, or it would pump the water to where it needed to be to turn into steam. And that's what he discovered through that. So the history of energy as a concept is basically energy as a system. So in summary, in regards to what energy is, in terms of the nature of it, it is that energy flowed within systems. So it flows within, so you have a system and it flows within it from one store to another store. And that it could be made to flow to other stores to do useful work. So therefore you could divert some of that flow to do some useful work, to do some other work than it was perhaps doing. But the most important thing that he probably discovered was that energy was just one thing. And that's important when we talk about the conservation of energy. You can't create it. So let's get that out of the way. You cannot create it. You can simply transfer it or convert it or move it or increase it or decrease it. But you can't effectively create it. You're basically moving it from one energy store to another energy store. And as I've said, it sat in many different energy stores at different stores, and it flowed on many different paths, but it was just called energy. So really important, conservation of energy. You cannot create and you cannot destroy energy. It merely is transferred from one store to another store. With the concept of energy described in terms of its historical significance, what we're now going to do, or what I'd like you to do, is on your sheet of paper, if we could draw a table, it merely be 2 columns, and it needs to have one heading called name of energy store, so that's just what the name of the energy store is, and then the description of it. Now, there are some energy stores that can be visualized through an object, okay, and we'll come to that in a second. However, there are certain other energy stores that are that you cannot place within an object, so they're unidentifiable as an object, if you see what I'm saying, and it will become much clearer as I go through. So what we are going to do over the next 6 to 7 minutes is that we are going to collect each of the energy store names and a description of what they are. Now, some of them, like I said, you will know, but some of them you would not have heard of before. And the definitions that I'm giving you is the definition of the energy store. Okay? So number 1 is the gravitational potential store. So you would just call it gravitational potential. And what is gravitational potential? To give the definition as per slide, it's the energy which is stored in an object raised up against the pull of gravity, and it exists for as long as the object is raised up. So if I were to hold and I've got my mobile phone on me, if I were to hold my mobile phone and raise it into the air, because I have risen it or raised it up in the air, that mobile phone has increased its gravitational potential energy store, and it is linked to the height. Okay, so it is linked to the height. The higher I move it, the higher I raise it, I should say, the greater the gravitational potential store. Okay, so you can see from the 2 images that you have got you've got a tower, you've got something being thrown off the tower here that I'm just circling, and then you can see it as A there. Which one has the greater gravitational potential store? It is this image here, because the height there that I'm highlighting as red is much greater than the height there that I'm highlighting in red currently. Okay, so because that height, I'll try and write a H, there we go, because that height is much greater there, it has a greater gravitational potential store at that point. Okay, at that point. And the boulder here in this image shows exactly the same thing. Because it is raised, this boulder has greater gravitational potential energy than that boulder within its store. Okay, so that one has more than that, and it's as simple as that. The second energy store is one that we probably have all have heard, however sometimes we may not conceptually understand what exactly it is. It's the kinetic energy store. Okay, so that's our second one, and that is simply It's the energy that's stored in a moving object for as long as the object moves. So going back to our boulder analogy, the fact that the boulder, and you can see in this image, is now rolling down the hill, it is probably accelerating its speed. Okay, so it's probably accelerating. Okay, I'll try and write it. This is what I'm doing on my mouse, by the way. So you can see it is accelerating down the hill. It is increasing its kinetic energy. Okay, it's increasing its kinetic energy because it's getting faster. So the faster it goes, the more kinetic energy is within its store. Okay, so there, and the same concept is with the snooker ball. So what you've got is, you can see the snooker ball is being hit here. It was stationary at one point. It is then moving in that direction. So therefore the kinetic energy store has increased. So it's moving. And as soon as it comes to a standstill, which is probably once it rebounds in, I don't know, in that direction, let's say. So it'll rebound and it'll end up here. It'll have no kinetic. It will have a zero kinetic energy store. But it will transfer all that kinetic energy into all these balls, and they will move off in their various directions. So as long as it's moving, and as long as the object moves, there will be a kinetic energy store. It might be high, it might be low. That depends on perhaps the speed that it is moving at. The third energy store is the elastic potential store. Now, the energy is stored in a stretched elastic band or spring. So I've given you an example of a catapult, for as long as these objects are stretched or compressed. Okay, so that's your definition for elastic potential. And if you stretch an elastic band, as this image is showing, what you are doing, okay, so once you stretch it, we all know that once you let go here, it will probably fly in that direction. Okay, as you stretch it, so you increase the elastic, I'm trying to write elastic potential, and I'll stop writing, I think, elastic potential store, as you increase the stretch of that string. Okay, string, what am I talking about? Elastic band. So as you stretch the elastic band, so you gain elastic potential. Now, out of curiosity, if you let go of it, the elastic potential store would rapidly decrease, and what would increase? Some of you may have got it straight away. Yes, the kinetic, because it would be moving. Because at the point of when you pull it and you stop, it's not moving. When you let go, it will start moving, and therefore you will see the kinetic energy store increase. So that's the elastic potential store. Number 4 is, and this is obviously not in any order in particular, number 4 is the thermal or internal store, and I'll come to the word internal in a second. Thermal store is energy stored in a hot object for as long as the object remains hot. Quite straightforward, that one. So that's thermal store. However, let's just think about it for a second. If you've got a hot cup of tea, as the image shows, it will be probably steaming. So here's your tea. It will probably steaming. Okay. The steam essentially represents the energy being exuded out. And what I mean by that is that you've got some thermal energy being released from the tea. Where does it go? Well, it goes into the surroundings. Okay, so that thermal energy store in the teacup is decreasing, and the thermal energy store in the surroundings, which we call the internal store of the surroundings, is increasing. Okay, so that's where all the thermal energy, and we sometimes use this word interchangeably with heat. Never again. We call it thermal energy store. We never call it heat energy store or heat store or heat. It's thermal energy or thermal energy store. That's what we need to start calling it. So that thermal energy store decreases and it's released into the surroundings, into the internal store of the surroundings. And what happens to the surroundings? The temperature would increase. Now, obviously, it wouldn't increase to the extent of the cup of tea, but it would increase overall. And that's what happens, say, for example, if you're in a room, say in the morning, you're in period 1, it's 8:25, it's freezing, the windows have been open, or the heating's not been on, you go into that classroom, immediately, oh, it's freezing in here. By the end of the lesson, you're like, oh my God, I'm sweating in here. And the reason why you might be hotter in there without the heating necessarily being on is that everyone in there, everybody in that room will be releasing their thermal energy from their bodies, and it will be going into the surroundings, therefore raising the temperature of the surroundings. That's why in a room full of people, it will progressively get warmer and warmer and warmer, because it just doesn't disappear. That heat that you feel off your skin doesn't disappear, it goes into the surroundings. Our fifth store is the magnetic store. This one is probably one of the most simple ones, and it's just energy is stored when two magnets are attracting or repelling for as long as their magnetic poles remain apart. So, you know, when you have two magnets next to each other but they're not touching each other, they kind of exert a force. Now, it might be a pull or it might be a push. I would tend to use the word an attracting force or a repelling force rather than push and pull, but that's probably a term that you have used, particularly in Key Stage 1 and Key Stage 2. But what we need to talk about is the ability of that magnet to attract or repel. Now, when you bring those two magnets together, depending on which poles you have, so if you've got two north, for example, they will repel. And you can feel it. You can, if you try to move those two poles together, it would like start circling around each other because you're trying to get them close, but you can't get them close. And then if you put a north and south close together but not touching, then you can feel that they're trying to move towards each other, and you physically you have to exert a force the other way to try and make sure that they don't. So you're trying to pull them back, so they're not attracting. Now, as long as they remain apart, there's a force. As soon as they touch each other, though, that north and south pole, there is no force. There's no magnetic energy store at that point. Okay, so that's the idea of the magnetic energy store. So the next one is nuclear store. This one's quite a simple one in the fact that energy is released within the nuclei of atoms, which can be released under various processes. Nuclear fission, which is generally what you get in nuclear power plants, particularly uranium-245, that undergoes fission. Nuclear fusion, and that generally occurs, well, it occurs in stars, to be honest, because you'll need a high temperature, a really high temperature, and you get nuclear fusion of hydrogen and helium occurring with that one. And then radioactive decay. And they're the three different versions of the nuclear store. Our penultimate store is the chemical store, probably the most prevalent one in terms of it's what we do. We require food, and within that food there is a chemical energy store that we then transfer into various other stores when required. So energy is stored within the bonds between chemical elements. That's in food, fuel, or batteries. Okay, so there's lots of uses here for the chemical energy store. The energy could be stored for as long as the food or the fuel or the battery exists. Okay, and that's the chemical energy store. Our final one is the electrostatic store. Now, that is where energy is stored between separated positive or negative charges that are attracting or repelling. Okay, so if I were to say that in a different way, the energy stored when like charges, so when two similar charges are moved closer together, or when two unlike charges are pulled further apart. Now, when does that occur? Well, I know last night I heard it. Thunderclouds. Yep, the fact that you hear thunder and the effect of that being from lightning, that is an electrostatic store that you can see there. A Van de Graaff generator, if you manage to see it, so you know the metal kind of semicircular sphere that you put your hands on and your hair goes up in the air, something that you should all have the experience of doing. A Van de Graaff generator would also do that. Now, the energy can be stored for as long as the separated charges exist. Sometimes it only is for minutes, sometimes for many, many hours. So that's the electrostatic force. Electrostatic store. There we have it. Our energy stores complete, our concept and our historical background to what is energy complete as well. I hope you enjoyed that quick run through energy for the last 25 minutes. Now, lesson tasks. As always, my lesson tasks aren't any different. Task 1 is to answer 10 multiple choice questions. That will be testing your recall on the key aspects of this first lesson. Task 2, in no more than 150 words, how the concept of energy emerged. Now, it's not necessarily that you remember the names, although it would be nice if you remembered the people who were involved. However, the idea behind it, that's what I want you to remember, because it's sometimes really hard, and I'm sure you found it from the start. It's really hard, and probably even now, it's quite hard to describe what energy is. But if you describe the process of how it came about, that goes into describing what energy is as a concept. Okay, so that's your task 2. Your task 3 is a research task, and I'd like you to find out, how does a steam engine work? Okay, so we spoke a lot about steam engines, and we spoke, and the idea of energy first came from looking at how steam engines work. So what I'm looking for is just a very simple explanation of how does a steam engine work? How did it work? Okay, so they're your lesson tasks. And the final slide is the summary note slide. What I've done is I've put the table completed now. So you've got all the energy stores: gravitational potential, kinetic, elastic potential, thermal, magnetic, nuclear, chemical, electrostatic down the left hand side, and then you've got their descriptions. You do need to know these. Can't move forward within the energy topic without knowing them, because then it becomes really difficult to describe and explain some of the energy transfers that we're going to talk about between stores in the next lesson. Right, I do hope you found this first energy lesson interesting, particularly the history behind it. If you do have time, do have a look at the people who are Leibniz, Young, and Carnot. Do have a look at them, have a look at what they discovered, have a look at what they wrote, and then you'll get a better understanding of the history of how energy came. However, in terms of what you need to know and what you need to do now, you need to go onto that Google quiz and then complete the 10 multiple choice questions and do task 2 and the research task if you can. I will see you for lesson 2 when we're talking about the energy store transfers. Okay, hope you are all well, and I will see you soon. Goodbye.